Have you ever stopped and wondered what it really takes to keep something cold? I'm not just talking about your lunchbox. I mean, hundreds of tons of food. Well, today, we're going on a hunt for heat to figure out exactly how engineers calculate the power they need to win that constant battle against warmth. All right, let's get into it.
And hey, this isn't some textbook thought experiment. This is a real-world problem, pulled right from our source material. We're talking a massive room, 225 tons, that's 450,000 pounds of frozen chicken, all sitting in the middle of that blistering Cairo heat. So this is the puzzle we are going to solve together.
So here's our game plan, our roadmap for this heat hunt. We're going to start with the basics, then we'll track down all the heat coming from the outside, then from the inside, and even from some places you would never expect. And finally, we'll put all the pieces together to get our answer, and we'll even take a look at a totally different way to cool things down. Okay, first things first, we need a really crucial mind shift. Refrigeration doesn't make cold. Cold is just the absence of heat. The real job of any cooling system is to act like a heat mover. Its one and only goal is to grab heat from inside a room and just dump it somewhere else.
And this is the classic machine that does the job. It relies on these four key players, all working together in a cycle. So the evaporator, that's inside the cold room, and its job is basically to absorb heat, kind of like a sponge. Then, the compressor squeezes the refrigerant gas, making it super hot. That hot gas flows to the condenser, which is on the outside, and it dumps all that heat it collected into the air. And finally, the expansion device cools that refrigerant way down, so it can go right back to the evaporator and grab even more heat. It's just this non-stop cycle of grab, squeeze, and dump.
So let's start our investigation. Our first and maybe most obvious suspect in this whole heat hunt is the world outside. You've got the sun, the air, the ground. They are all working 24/7, trying to warm up our nice cold room.
And heat's main way of getting in is through something called conduction. It just seeps through every single surface it can find. The walls, the ceiling, the floor, every part of that building is a potential doorway for unwanted warmth to sneak in. So how do you fight that? Well, engineers don't just guess, they calculate. And I know, this formula looks a little intimidating, but its job is actually pretty simple. It calculates something called the U value, and that's just a single number that tells an engineer exactly how good a wall, one made of concrete, insulation, and steel, is at stopping heat from leaking through. And this right here is a perfect example of why location is everything. The hotter it is outside, the harder that heat is pushing to get inside. So if you're designing a cold storage room in Cairo, you've got a plan for 41 degrees Celsius heat. But if you're in Alexandria, it's 37 degrees. That 4-degree difference might not sound like much, but it has a huge impact on the final power calculation. Okay, so we've accounted for the heat sneaking in from the outside, we've secured the perimeter, so to speak, but what about the heat that's already inside? Our investigation now has to turn inward.
It seems super obvious once you think about it, but it's a detail you absolutely cannot forget. Every single light bulb you turn on is also a tiny little heater, radiating warmth out into the space. Engineers have a name for this, the lighting load.
And it's not just the lights. People, we are basically walking, talking 37 degrees Celsius heat generators. So if you have workers moving in and out of that cold room, all of their combined body heat has to be calculated and then removed by the system. And yep, there's a name for that too, the worker's load.
All right, let's keep going, because this is where our heat hunt gets really fascinating. Beyond the obvious stuff, there are these hidden culprits that can generate an absolutely massive amount of heat.
Let's go back to our 225 tons of chicken for a second. Even if it shows up frozen, it might not be at the final target temperature of minus 18 degrees Celsius. So all the energy needed to pull that remaining heat out of the chicken itself, that's called the product load. And believe it or not, it can often be the single biggest factor in the entire calculation. But what if the product you're storing isn't frozen chicken? What if it's something that's still alive? For example, check out this diagram from the source documents for a cold storage room built just for apples. This brings up a completely unique and kind of weird source of heat.
And here it is. This is the wild part. Fruits and vegetables are still living organisms even after they're picked. They're still respiring, they're breathing, and that biological process creates its own heat, 24 hours a day, 7 days a week. Engineers actually call this respiration heat, and for fresh produce, it's this constant internal fire that the cooling system has to fight against.
Okay, wow. We've hunted down all our heat sources, the obvious ones, the ones inside, and the really surprising ones.
Now, it's time to add up all the clues and figure out the final cooling power we actually need. So this is the full list of suspects. Our engineer has to account for every single one of these. You've got the product load, the heat transfer through the walls, the air that rushes in every time a door opens, that weird respiration heat we just talked about, the lights, the workers, and even the heat coming off of motors on fans or forklifts. It's a lot.
But it all comes together in this pretty clear four-step process. First, you identify every single potential heat source that we just listed. Second, you use a bunch of specific formulas to calculate the load from each one. Third, you add them all up. And finally, you determine the total refrigeration capacity you need to handle that total heat load.
And here's how it all adds up in the end. The total cooling power needed is the sum of all those individual heat loads we found, plus a little extra. That extra 0.1 in the formula is a safety factor, usually about 10%. It's the engineer's way of building in a buffer, a little insurance policy for unexpected conditions, to make absolutely sure the system can keep that chicken frozen no matter what happens.
So, we've solved our puzzle. We know what it takes. But the story doesn't end there. All the systems we've talked about so far use compressors and pumps and moving parts. But what if you could get something cold with no moving parts at all? Get this. This idea actually goes all the way back to the 1800s. The basic principle is incredible. If you run electricity through a special junction where two different materials meet, you can make one side of that junction get cold while the other side gets hot. It's called thermoelectric cooling, and it's basically solid-state refrigeration.
And this gives you a great side-by-side comparison. On one hand, you have the conventional refrigeration we've been exploring. It's powerful, it's efficient, and it's perfect for huge spaces like our chicken warehouse. On the other hand, thermoelectric cooling is less powerful, but because there are no moving parts, it's totally silent, super reliable, and can be made incredibly small. That makes it perfect for things like those little portable car coolers, or for precisely cooling sensitive electronics. And that brings us to our final thought for today. We've seen the incredible, detailed science that goes into designing these massive cooling systems, but we've also seen the silent, solid-state alternative. So the big question is, as this technology gets better and more efficient, could we one day see a future where that noisy compressor in your refrigerator at home is replaced by completely silent, solid-state technology? It's definitely something to think about.